before we get started, every iterative function can always be written down in recursion. And also everything in recursion also can be done by iteration. It's proven, but not really 100% sure. Okay, it's proven. Somebody tried to prove that, but it's not 100% sure it will be true. Okay, but anyway, let's look at what it is here. So the first part, we have the countdown. Countdown means I want to count down some number. So given the n, I started to, each time I print a number and then count down. So actually I want to count down from, say, 10. So the first time I print out 10 and count down to 9, until it's 0, and then I say press off. So you count down to 0 and you press off. Okay? So like you get 10, 10, 9, 8, something. Continue until you have 1 and 1 call, count down 0 and count down 0 will stop, and then say press off. So here tell us one thing. In a recursive function is a function calling itself. Number one, recursive function is a function calling itself. Okay? A function calling itself is called recursion.
Okay.
Okay, so it's quite strange, but it's something like that. It's a function calling itself. It's called recursion. But okay, now for example, we have n factorial. We have n factorial, so we can say n factorial f of n. F of n, and then we say f of n equals n times n minus 1. So it actually is like n times f of n minus 1, right? Because f function we define as n factorial. So we keep doing that, But there should be an n. Should be an n. And here you need to define f of 0 or f of 1 to stop it. Some of the termination condition need to be done. That termination condition, we call it base condition or base case or base condition. In this case, base condition is 0. The rocket will blast up. Okay. Factorial, you can use f0 equals 1 or f1 equals 1, but either way, it will work. Okay, either way, it will work. Okay, so let's look at the factorial function in our project. So let's start it with this factorial function. So given that I have n equals 5, right? And I want to try a iterative function first. So I do this system.out.println, and I say I want a iterative factorial. So I have something called integer called the product. Okay, I must say Okay, that's product. I need to define integer I equals pardon?
Yeah, never mind.
Okay, something like that. Okay, and then system.out.println. Okay, that's done. That's wrong it. Okay, that's the first one. We have iterative function. Okay, 5 factorial is actually 120, right? So here, if I say it's actually 4, you got 24, right? This one is a iterative version. Okay, is this okay or no?
Yeah.
Okay, this one's okay. Now let me do some function that actually recursive. So let me do this one factorial 2. Wait, let me see. So let me do another function called factorial 2. And then I copy the whole thing over. And right here, I just passed. Okay, and I'm going to do it as a factorial function. A recursive function. So here I should define something called, let me use a simple name. Okay, so I will do integer f. Okay, I just want to use the simple f. Okay, so that's a factorial function f. And this one I'll take some integer n in here, and then I would return n times f of n minus 1. Okay, and here I'll say if n equals 0, return 1. Okay, that's recursion. So here I say n equals 4. I don't need all of these. Here I say is recursive factorial, and this whole thing I don't need it, and this thing I don't need it. Okay, and here I should say my percentage d, and then n product. Here I should have the percentage d for product slash n for change line, and I do this. Okay, and let me compile. What's the product? Oh, I don't have product. Here I should have f of n, and here I should put n. Okay, I'm sorry, I made mistakes. Okay, that's a 4 factorial, and then if I get it to be 5, the 5 factorial, it's 120. Okay, is that okay or no? So far, okay. Now this one is actually iterative. Let me try to find the iterative version as well. Public static integer f intn. Let me try to get an n and start it from here. So this whole thing is the same. So I just copy over, cut and pass here. I equals 1, product equals 1, same thing. Put it here. Okay, initially it's the same. And here I can actually get rid of the for loop. Let me do for loop. Get rid of the while loops integer I equals 1, I less than equal to 10, I increased. And this one, I don't need it. Right? This one, I don't need it. And this one here, I need to have a semicolon. And here, I return product. Okay? And here, again, I just need to copy this guy over. Yeah, if you are good at some programming, actually you can copy from something here, there, and then still make it work. Okay, and then you can improve with some new program, recursive version, iterative version for phi, right? In this case, you need to check if n equals 0, return 1, right? Right? You need to check that condition so that your f(0) will work for boundary condition. Okay, so this is one recursive version for factorial, one for recursive. Now we had two versions for the same function. And this countdown is easy, new line. You can have this function 3 line to call new line and new line call 3 times. That's easy. So we have n9. You can try to print n9 call itself until it's less than equal 0. When it's equal 0, it will stop, do nothing. So that's fine. This is recursive. Now the next topic is recursive stack diagram. So the next thing we will discuss, like, okay, both of them will work to give you some result, right? But which one will run faster? These two programs, which one will run faster? Any idea? For this program on the right for iterative, left side for recursion, which one will run faster? Okay, left side recursion look like simpler.
Factorial.
Right side iterative is more complicated, right? But who will run faster, in fact?
The one that's in front of the other one.
Which one? This one? The iterative one?
Yeah.
Why?
Isn't it because it's much simpler and it doesn't have to go through the calculation stuff?
This one?
Yeah.
And why this one won't? This one is simpler, it's shorter code.
But it has to keep running over and over again.
Yeah, but this one also need to keep running over and over again with the photo.
I don't know. It just looks less condensed.
It's not more natural to you?
I mean, like, it looks more condensed. The other one looks more condensed. Like,
yeah, this one left-hand side more condensed, yeah. But who will run faster? I mean, condensed is left side condensed. Recursion always more condensed than iterative. But right-hand side, I would say would be faster. Why?
because the variables are already given.
No, both of them you have a variable given as phi to start with. So that part is not a factor.
Because it doesn't have to go back and then like do all that calculation every single over again.
No, it's actually only calculation is multiplied by the next value. So that part is also not true. Okay, right hand side, of course, I told you the answer. Right hand side is faster. Not because of that, but because of this guy every time is only a for loop. This guy every time is a function call. So when you do function call, you need to go through main function and then f function of 5, calling f function of 4, calling f function of 3, calling f function of 2, calling f function of 1, calling f function of 0. And while the right hand side, It's only setting some value and multiply, setting some value and multiply. So this one, in fact, use less memory and also run faster. Because each time you have a functional call, it's like running, jump to somewhere, go back, and then here inside this loop, it jump to somewhere else and come back again. You know, and then each jump from one location to the other, you need to push all the parameter list from here. You need to push all the parameter list from the parameter list to the stack. That's what we call it stack. You keep doing that, and then once it's done, you pop out of it, pop out of it, pop out of it, pop out of it, pop out of it. So it's more work to be done by CPU because of the function call. And in order to understand what is going on in the stack, here we need to have this recursive stack diagram. So for example, original my function is main function. I call countdown of 3, countdown of 3, call countdown of 2, countdown of 2, call countdown of 1, countdown of 1, call countdown of 0. So each individual call, I need to push some data into system call stack. And then 3 call 2, 2 call 1, 1 call 0, and 0 return pop out from the stack. And 1 return pop out from stack, and then 2 return pop out from stack. 3 return pop out from stack. And then you pop out everything from stack. So more memory transaction, and more memory transaction means slower in program. Why is that? Because I have a CPU, right? If I am only doing for loop, integer assignment, and then increase and then multiply, my CPU keep busy, and then I just get some data calculated, get some data calculated. But if you have f of n times n some variable, then my CPU need to go through my system bus, go to my memory, get some value of n coming back. After calculations, right back to memory, back and forth, too much memory access. So it slows things down because of the CPU performance. Is that okay? And then the other one, the iterative one, I'm actually just using my CPU and some register to continue to calculate it. I have no need to access my bus. Okay, bus is off-chip operation. You go out of your CPU chip to do operation on memory. While on-chip calculation, multiply, everything can be done by CPU, same IC, same integrated chip to do operations. So iterative function usually have more advantage in terms of performance. But why we want to do recursion? Because of its simplicity. It's easier to understand and easier to write code. As you see right here, this recursion version, as long as you know my f of n equals n times my this one is the recursive equation. My f of my n band equals my n times n minus 1 band, right? I will be able to write this, and I know my 1 band, or no, my 0 band is actually 1. That's the whole thing I know. Base case is 0 band equals 1, and then recursive relationships, that is. While when you write this iterative version, it's kind of tedious. Okay, I need to remember initially my product is 1, and every time I time I into there. So my A naught is 1, my A1, I'm sorry, my S naught is 1, my S1 equals 1 times 1, my S2 equals 1 times 2. I'm sorry, this is S naught, this is S1. My S3 equals S2 times S2 plus times 3, something like that. So this one, iterative function is the same with the previous one. I try to write those exponential minus S squared things, right? It's more similar to that. You need to know the recursive relationship by coding into a loop. While this one, you just need to know about a function call and then know about a base case. You will be able to write out the program faster. And right hand side, you need to know about recursion and then put into a loop, each one do one recursion. So the two way of doing programming are different. Left hand side, faster encoding, poor performance. The right hand side, slower encoding but faster in performance. And which one's better? Hard to say. Some of the recursive function do too slow. People don't want to use it. And sometimes because it's fast in calculation, it actually helps people to do things faster. And actually also some problems suitable for recursion, some problems not suitable for recursion. For example, sorting is a recursion problem. So people use the recursive function to do quick sort, merge sort, different sorting algorithm. But for some case, actually recursion wastes a lot of time and actually cannot finish it, especially like Fibonacci number or those kind of things. Recursion too slow and doesn't get to the get things done faster enough. Okay, so this one we call it stack diagram. Each state diagram, when we have a function, say I have a main function, my main function call my f of 5. For my f of 5, I need to pass my n in there. The n right now is 5. And then my fi call my f of 4. My f of 4 at that time n equals 4. Something like that. You need to keep track of the n that you pass into the stack. And that stack is a memory model. And that's called this this thing we call it stack diagram. Okay, so let's stop this right here because in the AP course, this one will get much more deeper there. The next one is value returning method. Value returning method is I return some data from my previous function. So factorial, we finished that. That's value returning function. So that we done this, come down, we done it. Okay, so basically your main function called factorial 3, you reuse 2 and the result 6. Okay, 3 call 2, 2 call 0, 0, I'm sorry, 2 call 1, 1 call 0. 0 have factorial of 0, you get 1. 1 return to there, multiply with 1, so it return 1 back to here. 1 multiplied with n is 2, it becomes 2. Pass the 2 to here, 2 times 3, it becomes 6, it go back to main function. Okay, this is how the stack diagram do for the factorial function. Okay, and now the leap of phase. Okay, recursion leap of phase. So every possible function we can always do recursion. In fact, some we can also do some for recursion. Following the flow execution is one way to reprogram, but it quickly becomes overwhelming. An alternative way to understand recursion is leap of phase. When you come to a method invocation, instead of following the flow execution, you can assume that method work correctly and return appropriate value. Okay, this actually just you need to have some faith. Okay, when you do recursion, you don't actually trace down each individual code, but here you need to know, okay, I have my smaller case that will return me my n minus 1 factorial. So I have that, I calculate my current n factorial, just need to multiply by my previous result with this one. Then that's done. Okay, that's called, this one is called leap of phase. You need to trust your smaller case. So here is a function integer, has only one digit. It's a single digit. You give a number x. You need to trust it because you need to be greater than minus 10 and then less than 10. If that x is an integer, then that is a single digit. Okay, and then n factorial, this is fine, this is fine. Fibonacci number is your f of n equals f of n minus 1 plus f of n minus 2. That's called Fibonacci number. And that one actually is a poor function you will explore. And usually people use that to show the inefficiency of the recursive function. So right here, I'm going to jump from the textbook to somewhere else, okay? So this one, I'm not going to follow it now. The next one I'm going to do is sum function. Okay, sum function is, I'm going to do a sum function right here. Say, I am given a number 5. I want to calculate the sum of 1 to 5. So if, for example, I have an n, right, equals to 5. I want to calculate some number called sum of 5 from 1 to 5, okay? From 1 to 5. So here I have a function called public static void. I'm sorry. It's a public static integer sum. Okay, integer n. If I get an n, I should get a sum of n out, right? So my sum of n and my sum of n minus 1 relationship is what? Is return n plus sum of n minus 1, right? And with stable phase, that is true, right? My sum of n 1 to n is equals my sum of n to 1 to n minus 1, and then plus n. And then if n equals 0, my sum of 0 is what? My sum of 0 is 0. That's it. That's all only thing I need to know.
So what does the return, like the return just makes it like equals 0, right?
Return, that's called base case. When you have the n equals 0, that's base case. This was called.
What's the return for? Like, why don't you just write?
Return means that the 0, when you have a sum of 0, this one will get 0. Sum of 0 will get 0, and then you would, who will call sum of 0? Sum of 1 will call sum of 0. So at that time, n is 1. So 1 plus 0 is 1, so 1 will return to a sum of 1, and sum of 1 here would have n equals 2 for sum of 2. So sum of 2 is 2 plus sum of 1. Is that okay? So this thing, actually, I would have
So for these things, does it does the tiny classes first, and then it does the main class?
Yeah.
Or does it do the main class and then it calls on the smaller classes?
You build up the smaller case before you build up the whole thing.
I mean, like when you call the smaller case, like public static sum, when you call that in your main case, does it do it? Does it do that part of the code then, or does it do the main first, or does it like the program?
You do the main first, but actually you want to do the programming from the smaller case first. Okay. The execution flow is from the main function to call sum of 5 call sum of 4 call sum of 3, something like that. But when you do coding, you work on the smaller case first. The recursive function, this is recursive relationship. Okay.
Which ones?
I'll give you the sum of 5. Okay, so if I change this one to say 10, I should keep 55. Okay.
Well, so it does. So this does 10 plus 9, 8, 7, 6, 5, 4, 3, 2, 1.
Yeah. So
And
sum of
what's
10.
the 0, 0?
Sum of the 10 over here would be, sum of 10 would be 10 plus sum of 9. Sum of 9 code here, it would be 9 plus sum of 8. Sum of 8 here would be 8
okay.
plus, and then keep going down until sum of 1 would be 1 plus sum of 0. Sum of 0 come here, it would be n is 0, return 0. So sum of 0 is 0. 0 plus 1 is like, okay, let me draw some diagram to help you.
Oh, okay, so return
So
0 just
say
means
I
to
have a
stop.
sum of 3, right? It actually is 3 plus sum of 2. Sum of 2 is the 2 plus sum of 1. Sum 1 is 1 plus sum of 0, right? And then sum of 0 got a 0. It actually returned 1, and it is 1. 1 plus 2 is 3, returns 3. 3 plus 3 equals 6, returns 6. And then this one got 6. Now, you have a factorial and this sum. You look at the left side and look at the right side, what's the difference? There are only two differences. The factorial function and the sum function, only two differences. This guy and this guy.
That it, oh, yeah.
Right?
Yeah.
Structure-wise, it's actually the same. This guy is summation I equals 0, I to n. This one is called product of I equals 0, I to n. This is called n factorial. This one is sum of n. Okay, mathematically it's written like this. Here, it actually told you, it's leap of faith. You trust your subcase without questioning.
Okay.
You trust your sum of 0. If you are sum of 1, you trust your sum of 0 to return me some faithful value of the sum of 0. And then I just add my 1 into there. Same thing, my sum of 5 would trust my 5 plus sum of 4. Whatever value returned by sum of 4, it would be sum of 4. You trust it. And then I plus a 5 with it, it will be sum of 5. You know what I'm saying? Oh, but let's do this. Can you do like, okay, if we have a sequence, we say 1, 2, 3, 4, 5, right? This one we have A sequence, right? It will be A1, A2, A3 in math, right? So actually you can think about in Java is actually A0, A1. So the index is slightly different, but it's okay. In math, usually we starting from 1, but in Java we starting from 0. That's fine. Okay, that's fine. That's assume that there's not much trouble here. So that's using the mathematical term. Okay, that's using the mathematical term. So each one we have a series that would be 1, 2, 3, 4, 5 something. Okay, that's okay. So then A1 will be 1, A2 will be A1 plus 1, A3 will be A2 plus 1, right? Is that okay?
Yeah.
So this one actually is what? This one is, what's the term for this one?
The term?
Yeah, the term, terminology.
Isn't that just like the third?
Terminology.
I don't know. I thought we just called like the
This one is called recursive formula.
Oh wait, yeah, okay.
An equals An minus 1 plus 1, right? It's called recursive. So since you know this, actually you should be able to make the recursive quite well. You have the A1 that is actually equals 1 as base condition, base. Right? An is An minus 1 plus 1. right?
Yeah.
Yeah, this is the base. This one is the same with recursive function we have. So what you should be able to make this easier. So that one is a base condition. It's the same as the that one, a equals 0, and then we return something. So let's do this, okay? Let's do this. Since you know this, that's fine. I saw that you're still at the algebra 2 or some other level and you don't know. Since you know pre-calculus, that's better, okay? So let's do our Java stuff. So now I'm going to try to create the series, okay? I'm going to create a series. So now we are on chapter A. So let me pick up your one. So here, Ethan, rules A, chapter A, okay? Now, I'm sorry, so let me just close it. Okay, we open this one. Okay, last time we work on this, right? So here, let's do sequence. So let's call it A, okay, really call it A. Now, get rid of this. Get rid of this. Okay, so I have this one called public static A function. And then here I have integer I, right? So this one actually is a function, but it will give me what? It's a function, it will give me A of I or AI in your mathematical term, right?
Mm-hmm.
And in order to make it more like a math, okay, so right here actually the base case is if I equals 1, return 1, right? Other case you have recursive condition, so it actually would be call it A I minus 1 plus 1, and then I just return this value. That's it. That's what your series is. That's what your series is. And right here, I just need to put return for integer. Okay, so now I actually do this. Now I actually do this like here, system dot out dot print. Okay, and I say A of this equals plus A of I, okay, and here I need a I and A of I. This one I change it to F, okay, and right here I have another percentage D, okay, and then press /n, okay, and here I say system dot out dot print /f, okay, and then here that's what I work on the single one, and then I say I equals starting from 1, I less than 11, so I will go from 1 to 10, and each time I print out A of I, right? So this one actually is this. Since you have a pre-calc level, so that will give you this. Pretty simple. A of I equals I 1, 2, 3, 4, 5. You know? So this line is nothing more than telling people, this one is nothing more than telling people A1 equals 1. This one nothing more than AN equals AN minus 1 plus 1. Why? Because if you have an A of 5, right? So A of 5 equals, you call it A of 4, and then plus 1, right? So it's A5 equals A4 plus 1. So AN equals AN minus 1 plus 1. So the recursive function is nothing more than the recursive formula in math. Is that okay? And then the sum function we talked about last time, sum of n whatever, is actually summation I equals 1 to n for I. I actually represent this. Whatever I roll before is actually the series. Is that okay? It's actually a series.
Yeah.
So if you think about it this way, it's actually not that hard, okay? Read this again, okay? Read this again. This one, when you return 1 means what? This one is I equals 1. That actually means A of 1. It actually A1 equals 1. This case tell you A of I equals, that's the A of I is what you would like to return. Actually A of I minus 1 plus 1. Nothing more than that. It's just this simple.
Wait, what? So it's saying that if I equals 1, then
you will get 1. That's what the first statement say.
But I thought return means finish end equation.
The return actually means, actually A is a function, right?
Yeah.
A cell is a function, right? So you have A of 1 means the return value is 1. So if you assign to Y, Y will become 1. So actually that means A of 1 is actually 1. Because it's a function, you return that will return to Y something that get a value outside. Right? Same thing if you have like A of I, right? And you assign to some value Y, but that A of Y is defined by this return.
Oh, it's for A. So the I equals to 1 is for I. And the return 1 is for I, and return A, that thing is for A.
Yeah. Okay. So this one, two of these, one is for recursive formula, one is for base case. That's it. Nothing more than that. So if you know this sequence, it should be easy to understand. Know about sequence, it should be easy to understand this. Okay. Okay. Now let's call recursive. Recursive, you only need to set up current index and then your base condition. Some people call it termination condition, and then the recursive function. Recursive function actually is a recursive formula. Okay, that's recursive function. That's what we talked about last time. Okay, now let's go back to math. Okay, so you actually have this one called, you usually, today I'm going to focus more on math. You have this one called A1 is equals 1, right? So now if I have a series 1 plus 2 plus 3 plus 4 up to n, okay? And then to take this one, let's call this one a series n. That actually means summation of I equals 1, I to n, right? And this whole thing, when we take the sum, there's a one way I can do it. It's like n minus 1 plus this plus 2, 1, right? And then this one sum together, that actually is 2s will be, 2sn will be n plus 1 plus n plus 1 plus plus n plus 1. And then it's totally n times. So 2sn will be n plus 1 times n, right? So Sn will be half n times n plus 1, right? We call it series. That's if we actually calculate by formula, right? If we calculate by formula, it would be something like this. Now, if we use for loop, it will be what? If we use for loop, the series n will be for integer I equals 0, I less than equal n, right? And then I increase. The 0 doesn't matter because 0 you sum it up, it doesn't matter, right? So here I would say Sn plus equals I. So each time if originally I set Sn to be 0, and then each time I add my number I into there, right? Until it equals n. So eventually I should get Sn equals 1 plus 2 plus blah, 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 plus 2 n, right? Is that okay? The first way by formula is half n times n plus 1. Second time I use this for loop, it actually each time I add my I value to my sum, right? So I started from 0 to n, but 0 actually doesn't matter. You can start it from 1 actually. It doesn't matter. That's your base case. Okay? Is that okay so far? Is that okay so far?
Yeah.
Yeah.
Okay. Now, let's think about this. Sn is also a sequence. So Sn actually sum from summation of I equals 1 plus blah, 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 plus n. This one is also a sequence. So Sn equals Sn minus 1 plus 1. Plus this guy n, right? Is that true? Yes or no?
No.
Yes or no?
Yeah.
Right? Your summation up to here, that's S minus 1, right?
Mm-hmm.
So that's true. Okay, this recursive formula you already found is recursive formula. Is that okay? This one is your recursive formula already. Now, in order to do a recursive function, I just need to find out the base case, right? So basic case is S1 equals 1, right? Sum of 1 is equals 1. But that doesn't matter. If I set the base case as S0 equals 0, that's the same. Because S1 is actually equals 1 plus 0 is actually still 1. Is that okay? Is that okay?
Yeah.
So this one actually I can just forget it. My base case become this one. My recursive function is here. Right?
Yeah.
Yeah. If you agree with this. Are you any more question?
No.
Okay. If this is fine, let's go back to our program we run last time. Take a look at the sum. Take a look at the sum. Sum is actually Sn now. Take a look at this sum. Sum is Sn now. So this one actually is telling you S not equals 0. That's our base case. This one tells you Sn equals S of n minus 1 plus n. Isn't that the two equation we have? Base case and recursive formula. That's it. Right? You trust your mathematical formula, then you should trust this function. When you do programming, you know, okay, I know my math is like this. Okay, I put it into the equivalent program. I will calculate my math. Then you should have the same face for it. It's called leap of faith. You have to trust it. You have to trust it. My base case, I said it right. My recursive function, I said it right. S of 0, when I get a 0, I get 0. when I get the S of n, it will give you n plus S of n minus 1. And then why should I worry about anything? Nothing to worry about, right? Because S series itself is another sequence, right? Is that okay?
Yeah.
Yeah? Then why should I worry about it? Right? So that's just basic sum is like this.
Yeah.
Okay? That's just basic sum is like this. That's called sequence. Another one, product or factorial. Okay, that's no, it doesn't call us, it's not actually, you can think about it, it's again, it's similar to sequence. Okay, so I have actually this one, I use this equation, pi equals 1 to n for each one. This means 1 plus 2 times 3 times 4 times 5 up to times n. So my base case, that's called product 1, would be 1, like only 1 times 1, okay? And then I have product of n equals product of n minus 1 times n. Factorial. Actually, you have n factorial equals n minus 1 factorial times n. I'm sorry, it's out of box, so I put it here. Then this one is product of n, this one is product of n minus 1. Nothing wrong, right? Same thing, you have a base case and you have your recursive function. Is that okay?
Yeah.
Yeah? Okay, if you agree, let's go back to our program. So that's nothing more than that. You just every time set out the base condition, set out the recursive function. That's it. Oh, I'm sorry, this one is actually a non-recursive version. This one is recursive version. Same thing, nothing different. Your base case, okay, you actually have that actually, let me explain. You had the, I'm sorry, you had a product of 1 equals 1, right? But if I set up product of 0 equals 1 as well, so product of 1 will be equals 1 times 1, right? And you have product 0, this one is product of 0, and it's actually 1. And product of 0 is actually 1. So this one actually same thing, you have product of n equals product of n minus 1 times n. So this one actually useless, just forget it. Just erase it. So that's a basic definition that 0 band is actually equals 1. Same thing, this one's your base case. You can actually write n equals 1, return 1 is also fine. That means p1 equals 1. But it doesn't matter, you put a p1, p0 equals 1 is the same thing. And over here, same thing, your n minus 1 factorial times n will give you n factorial. Right?
Yeah.
And you have to trust it. You have to trust it. Your p0 equals 1, your pn equals pn minus 1 times n. Then that's it. That's it. That's the whole thing you need to know. Recursive function, formula, and your base case. That's your recursive formula and your base case. That's it. Nothing to worry about. So recursive programming is to break down a recursive programming. Whole thing is actually find the termination condition of base case. That's the number one thing you need to do. Second, break down your larger problem into smaller one, and then find out the recursive relationship. That's all you need to do in recursive programming. That's all you need to do in recursive programming. Is that okay?
Yeah.
Okay, that's recursive. But here today, let me teach you some math. I don't know whether you know this or not. Let me continue on some math. Okay, right here, summation of I from 1 to n for 1. What's the value? What's this sum? Still remember that or no? What's this value?
Isn't it like 1?
What?
Isn't that 1?
This one is not 1. This one equals n.
I mean, yeah, okay.
It's actually 1 plus 1 plus 1 plus 1 plus 1 plus 1.
Until it reaches n.
Totally n. Is that okay? Is that okay? How about how about this? How about summation I equals 1 n and this one 2?
Isn't that n also?
No, this one is 2n.
Yeah, okay.
So I mean, it actually equals 2 plus 2 plus 2 plus 2, totally n of 2, so n times 2 is actually 2n. Okay? Now actually 2n. So here I give you one thing. I equals 1n for 1 equals n. Summation of I equals 1 to n for 2 equals 2n. Summation of I equals 1 to n for constant c. What's the value? Any number c.
Cn.
Yeah, this one is cn. Good. So this one tells you is something like this. Okay. This one is order 0. Okay, order 0 I teach you already. Summation of 1 equals n. Okay. So summation of c equals nc. Okay. That's the summation. That's the order 0. Now I'm going to teach you order 1. I'm going to teach you order 1. Order 1 is, let me see. Okay, I think you probably know it or maybe no, I don't know. So summation of I equals 1 to n I. What's the value?
In.
What's the this? That is the sum 1, 2, 3. We just calculated, right? It actually n times n plus 1 divided by 2, right?
Yeah.
Yeah, we know this value, but I'm not going to stop here, okay? We know this value, but what I'm trying to do is not like this, okay? It's not like this. Right here, let me call this one as S, okay? So let me do this. I have n plus 1 square equals n plus n square plus 2n plus 1. Is that okay or no? Yes or no?
Yeah.
So, okay, since it's yes, you approve it. So 2 square equals 1 square plus 2 times 1 plus 1. Is that okay?
Yeah. Wait.
3 square equals 2 square plus 2 times 2 plus 1. Is that okay?
Yeah.
Continue until n square equals n. Let me see. No, this was not n squared. Let me do it.
N plus 1, right?
Yeah, this left hand side.
You forgot.
This left hand side, let me pick.
Wait, how did you get 3?
3.
Shouldn't it be 1.5?
What?
I mean, not 1.5. Shouldn't it be
3 squared equals
yeah.
this? Is there anything wrong? It's just
Never mind.
replace n by 3. Is that okay?
Yeah, sorry.
No, replace n by 2. I'm sorry. Is that okay? So n plus 1 equals, let's copy this one down. Okay, copy this one down, okay? And then you take summation for all the equation, right? You take a summation for all the equation, you cancel this out. This left-hand side, you have n plus 1 squared equals 1 squared plus 2s plus n. This one is summation of 1. You got it already? This one's 2 times summation of I. This one, s. What is the whole column? This whole column is 2s. Is that okay?
Yeah.
Okay, so actually on the right hand side is 2s plus n plus 1, right? So actually n plus 1 squared minus n plus 1 equals 2s. N times n plus 1 equals 2s. S equals n times n plus 1 divided by 2. So that's actually give you the summation I equals that equation. N times n plus 1 divided by 2. I call this order 1. Okay, that's order 1. Is that okay? You know that equation, but I just use in different way to prove it. I don't know whether you know this way of proving or not, but if you know, let me know, but I will try to lead you systematically solving problem. Okay, now I have a question for you. I have a question for you now. If I started from, say, if I actually started from 1, right? Give me the sum of 1 plus 3 plus 5 plus blah, 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 plus to like 25. Odd number from 1 to 25. What is the sum? Can you analyze this one and tell me how to calculate it? Can you analyze it and calculate it? You know how to do this one? If you don't do like using calculator summing it, how can you solve this problem? It actually is the summation I from 1 to I, let's say minus 1, right? One moment, let me take a call, okay? Hello? Yeah, and then this one, you need to calculate what n is right here, right? 25, this one 0, so it actually, this one is minus 1. 21 minus 1 is 26 divided by 2. You end up with 13, so this one is 13. And then what's the sum of these? It actually equals 2 times summation I equals 1 to 13, I minus summation I equals 1 to 13, 1. This one is 13. This one is what? Using this formula. Right? So you end up with 13 times 14 minus 13, right? So it actually is 13 squared. What I'm going to tell you is, actually this one, summation of I from 1 to n, to n, 2I minus 1 equals n squared. R number sum up to the ith term equals n squared. But actually from this one, what I am trying to do is like, no matter what polynomial you put here, there is a solution. We can systematically solve it. So this is only order of 1. We end up with this equation, right? And then we can continue to do order of 2. So let me clean this. It's a little bit dirty here. Let me clean the whole thing. Okay, so now we have 0 order summation of 1 equals n. First order summation of I equals n times n plus 1 divided by 2. Now, what's the second order summation of I squared? You remember the equation? It's 6 n times n plus 1 2n plus 1. What about summation I cube? It's actually n times n plus 1, n squared times n plus 1 squared divided by 4. This fusion you have to remember. You really have to remember this different equation. But here, I'm going to teach you how to actually derive this and derive this. Have somebody taught you this or no?
Yeah.
Yeah, you learned this before?
Yeah, I think, yeah.
How to derive these two equations? Say summation of I squared, summation of I cube.
How do you like
Derive this equation.
Oh, I forgot how to write this.
What?
I forgot.
You forgot, but someone taught you before?
Yeah.
Okay, you better need to review, okay?
Yeah.
You need to review because this, okay, what I will tell you is actually, okay, it's okay to forget something, but okay, right here. Same thing, I have the n plus 1. The last time I used square, right? Here I use cube. Equals n cubed plus 3n squared plus 3n plus 1. What's this for? What's the name of this? And then if I have the n plus 1 core, and then I have some formula. What's the coefficient of this? It's called. What's the formula of this? It's called binomial theory, right? Binomial theorem. It's called binomial theorem.
Mm-hmm.
Have you heard this before?
Yeah, where you like they take it. Yeah.
Yeah, I think you probably learned a lot of these things, but make sure you practice more, okay? You make sure you practice more, so don't forget it. Especially you are going to take AP call, okay? And then okay, this one, okay, whatever. This one, if we have a 2 cube equals 1 cube plus 3 1 square plus 3 1 plus 1 3 cube equals 2 cube plus 3 square 2 square plus 3 2 plus 1. Same thing, n plus 1 cube equals n cube plus 3n squared plus 3n plus 1 summation Q, and then n plus 1 q equals 3. This one called summation of I squared plus 3 summation of I plus summation of 1. Right? And then we have the first order equation. We have this first order equation, 0 order equation. We have this as a, and then we can solve this. Right? And using binomial theorem, in principle, you can all use like whatever n plus 1 to the power of something to solve all of these series. Is that okay? I don't want to go further. It will be repeating and similar. Is that okay so far with this?
Yeah.
Okay. And then if that is okay, then basically I'm telling you. So basically I'm telling you like, give me a some sort of equation summation I equals 1 to n. ai to the power k plus bi power k minus 1, blah, 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 plus the g or whatever, the last coefficient. It would be summation of I equals 1 to n. Any polynomial of I should be able to solve its equation. Right? With that, I plug into my loop. When I do loop programming, it will be much faster. Is that okay?
Mm-hmm.
So I don't know whether you still can figure out those equations or not, but try review it, okay? Try review it. Try review your binomial theorem. Try review your binomial theorem and then try to review your series.
Mm-hmm.
And deriving those whatever arbitrary polynomial, taking sum, you should be able to solve it. Okay. So here, for example, if I give you another question, like minus 5, minus 2, and then 1, each one separated by 3, right? Up to something called like let me see, 10, and then 10. Okay, let's do 19. What is the sum of these? Can you find out a formula? It would be summation I equals 1 n, right? Here is minus 5, so when you have I equals 1 is minus 5, right? So and each time you separate by 3, so it's a 3i minus what? 1 is actually 3, so it's actually 3i minus a.
Mm-hmm.
Totally how many turns? 19 minus 1, 2, 3 minus a, so actually 19 plus a, 27 divided by 3, this term is 9.
Yeah.
And then it becomes 3 times summation I equals 1 to 9, I minus a times 9. Okay, and then solve it. Is that okay? Yeah, so but practice this, okay? Practice this. So that you are not fast enough in doing this. Okay? And that actually will, based on the concept of, why I spend time for doing this mathematical derivation for you, because that's actually the root for recursive function. Okay, that's the root for recursive function. And then that state function I talk about, we cover this, right? So last time where we stop? We stop at this binary system. So by introducing recursive example to whatever, okay, here is a binary recursion. So what's that? So binary recursion, if we have 23, we try to get all of its coefficient. It actually can be done by a recursive binary function. Binary method, let me see. Okay, here actually is a display binary value. Okay, let me print up the example code. Okay, let me print up the example code instead of reading its statement so much. Actually, it's wasting time. Let's just look at the code. It would be easier. So lecture. I'm sorry. Wu J. Example chapter 8. Let me bring up this. Okay. Recursion. There's a countdown example. N9 forever. This is the whole. So here has a display binary. So if value greater than this one 0, display binary divided by 2, and then print out the modular. And then let me see, is there any main program? Okay, is right here. So what actually I don't want to do countdown. So let me actually take this one out. Okay, I just want to do this display. I just want to do this display binary. Okay, so right here, basically it has a display binary. I'm trying to display the binary term for 23. So let me compile this one. And then this one is recursion. Let me run it. So 23 would have these. Because of what? Because we do the conversion for binary. We had 23 divided by 2 is 12 remainder 1, right? And then divided by 2 we have 6 remainder 0. We have 3 and 2 and 3 remainder 0. And then divided by 2, 1 remainder 1. So it's 1, 0, 0, 1. Let me see wrong. This one, 23 divided by 2. Oh, I'm sorry, I made a mistake. I mean, redo it, okay? I made a big mistake. 23 divided by 2 is 11 remainder 1. 11 divided by 2 is actually 5 remainder 1. 5 divided by 2 is actually 2 remainder 1. 2 divided by 2 is 1, 0, so it's 1, 0, 1, 1, 1, okay? So what happened is like, what happened to this is like, okay, so each time actually right here, I got the number, right? I got a number 23. I got a number 23, right? So if this number actually less than or equal to 0, if it is 0 or less than 0, say that's as soon as 0, I do nothing. Means what? Means at the end I have the 1 and I divide it by 2, it actually end up with 0. Right? And then I actually don't need that. So that one actually I will stop there. Okay, now I will stop there. So what happened is like, here, if I got a 23, right? And then I continue to do division. Right? I continue to do division. So I divide it by 2, and then it's 11. This value, I take modular by 2. It actually is the last one I will display. So what happened is like, here, let me clean this up. It's a little bit confusing right here. Let me change to full color. Okay. So initially I call display of 23, right? So what I'll do is actually first, eventually I will display this 10 modular 2 that will actually is 1. Will display 1. Okay, let's assume that this eventually will display 1. So you will do the division of 11 first. So it's 23 divided by 2, 11 remainder 1, 2, 5 remainder 1, 2, 2 remainder 1, 2, 1 remainder 0. Okay. So what happens is that I have a display of 11, and then when I finish calling, I will display 1. Okay, and then this one is display of 5. When I finish calling, I'll display print 1. Okay, and then when I continue to call D of 2, when I finish, I will actually print out 0. and then d of 2, I continue to call d of 1, right? And when I finish d of 1, I actually will print 1, and then I will call d of 0 because I divide by 2, and that one actually do nothing will stop. Do nothing will stop. So then 3 of 0 stop. So my d of 1 will print out 1, and then I go back to d of 2. D of 2 print out this. D of 5, they print out this, print out this, print out this. So eventually it's like this one, print out in that order. Is that okay?
Yeah.
So that's this one called display binary. That's this one called display binary. But display binary, I have different way of doing it. Okay, I have different way of doing the display binary. Let me do this. I display binary 2. Okay. So here I have an integer x equal 33, right? And then what I'll do is like while x are actually greater than 0, right? And here I would have something called string result equals empty string, okay? And then each one I have integer d equals this one x take modular by 2, okay? And then my string result will have my result plus my number. My number actually my new number actually will add to the front. So I'll do this empty string plus d plus this. So my first one, I will add my last one in. The first, so first one, I will divide it by 23, and I take the modular, that's 1. That one, I will move it to here. The next one, 11, remember I put it in front of it. So that's a new digit I will add on. Okay, and then with that, with this one, actually, I would have x equals x divided by 2. Okay, and then at the end, system.out.print9. This one I will put result. Okay, let's try this one. Right? It's the same. It's actually the same. This is an iterative format, but it's actually the same. So now let me do this. Let me actually copy these things, and then I put into a function called public string. I need static string right here, and the integer x right here, and then put the whole thing over here. Okay, and then I don't need to have that x equals 23 now. And then this one I don't print now, I actually return the result. Okay, so here this one's string, I need to call the function display binary. Okay, and the whole thing is here I need to have return value, return the result, and here I clean the whole thing up, say system.out.print, and right here backslash f. Okay, and then right here I have system.out.print line, and then here I print f. and then here all this, and then binary of percentage t equals at the end I need to put /n. Here I have another one called percentage. Let me see. I want it to be binary. Okay. And then here I have my number 23, and then display. I mean, this one is not B, actually it's S. Okay, a string. Display binary of 23. Okay, so with that, compile. Let me close this one. This one is in iterative format. So I actually print out binary of 23. That's display 23, and I put a 23 in here. Initially, I set my result to be 0. When it is greater than 0, I actually take last digit. That's a binary bit. Either 0 or 1, right? And then I display that. So originally my result is empty, so I would just add my 0 or 1 over there, and then I have an x divided by 2. So then actually I take the last bit out already, and then I divide by 2. So it's the second last bit will be added in front of the last bit. Okay, something that I continue to do that, you will actually eventually will display. You will display the binary value. So now let's run it. Okay, that's binary of 23. So here actually I can do actually for loop integer I equals 0, I equals 1, I less than 25, I increase. And then here, instead of putting 23, I put I, and I put I. So here actually I can also do this. In order to prevent that to happen, I can actually do if x equals 0, return a single 0 for it. In case that you go into loop and it do nothing, okay, it do nothing, I can do this. And then here I can change I to 0. And then I say, okay, let me give me 5 bits. So it's actually up to 32. Okay, so I compile. And then let me compile. And then let me see. Right here, let me actually run it. And then this one is, let me see. Oh, okay. So this one is something like this. Is that okay? Is that okay?
Yeah.
It generate all the binary value. Okay, and then if I actually not happy about it, here I won't have like a bit, and then with z in 0. Let me see whether this work or not. Okay. Oh, it doesn't allow this. It doesn't allow the flag to be 0 over there. Anyway, that's fine. So it actually not allowing this to happen. Okay, so one way to do it is like I can actually do this string. Let me see. So I can do this integer that pass int. And no, I don't want to do it. Let me see. Okay, this convert to 8-bit format. Well, but this one is not really a good way of converting it. Okay, I just try to come out with something that actually will work to convert to 8-bit format, but that really is not a good way. So actually I'll comment that out. Leave it here, but I will comment it out. That's really not a very good way of doing things. So put aspect, and then here I leave it as this. Okay, so basically you display that number converted into a string format, and then it's actually in binary format. Okay, so it actually display in binary format. And each one you can either do this in the way that the previous one do, or this way using the while loop. Using the while loop and the previous example we see in this chapter A recursion function. This one, two work the same, but I think this one display binary is a little bit shorter in code. Okay, it's shorter in code, but again, this one could be slower as well. Okay, so that actually we have finished this recursive binary method. And then coding pad problem, you can go to coding pad problem for this coding pad problem. There's a website, okay? So the coding pad, actually, I want you to do it yourself. Here's a coding pad website. I probably told you already. There is an AP coding pad you can work on, okay? But this one, I would suggest that you wait until you finish the AP course to work on the AP set. Now you probably can work on the warm-ups part. Okay, and then finish all of them. Save the recursion, you can do it here, and save the AP until you want to test the AP. Okay, don't try that one right now. You will waste it, and you probably cannot solve all of them as well right now. Probably too hard. So starting from warm up part for that coding pad, for the coding pad. Wait, I actually need to go back to my lessons. So that one's a coding pad. You have tons of problems you can work on. Okay, I don't want to do it for you. Okay, this part actually we still have time. This part we finish this course. So again, try to work on chapter A for the exercises. You know, now let me talk about something else. Okay, let me talk about something else. So far we work on this. Standard recursion version. The next one, I'm going to tell you, teach you something called helpers. Okay, helper function. Helper function. Okay, something called helper function. Helper function can create tail recursion, and it will be faster. It will be faster with tail recursion. And first, let's talk about what is tail recursion. What is a tail recursion? Tail recursion function is a recursive function that when you do recursion, you have the this one return f of n minus 1 plus n or minus n or something. That is not tail recursion. Okay, that's not tail recursion. A tail recursion function is at the end, you just return, at the end of the function, you should return something, that has no more operation. So you can do f n minus 1 something inside here, but after that, you don't do one more operation to finish that your code. This one is called tail recursion. Is that okay? Is that okay or no?
Yeah.
That's called tail recursion. So tail recursion function is a function that you call a sub-function, and then the return of the sub-function is the return value for you. Okay? And a normal recursion, you may need one more additional subtraction or multiplication. That's not tail recursion. So now, since we finished the sum function, let me write a tail recursion version of the sum function, okay? I'll do a tail recursive function of sum. So let me call this class called sumR, okay? Instead of doing that original function, that's called sumR. So there's a new version of the sum function. So here, let me do this one, public static integer sum. Okay, here I have integer n, and I have integer s. Okay, so if n equals 0, return s. Okay, and then actually, let me see. S equals s plus n. Okay, return sum of n minus 1 s. Okay, let me see. If I have a 10, I call 9 and sum. Okay, okay, this is fine. Then I have a public function, static void, and then here, no, here I have a public static integer sum of integer n. Okay, and this one return sum of n 0. Okay, and this one public static void name 3. Okay, and then here system.out.println. Here I keep it sum of 10. Okay, this one is a tail recursive function of. Let me change the name. So in the future, you will remember. Okay, R is not a name easy to remember. Wait. Oh, got 55. I should clean out everything. This one is called tail recursive function. Okay, and this one is 55. You got it. Okay, now if I change to 9, it should be 45, right? Let's try. So let me do this. Sum of percentage d equals percentage d slash n, and then here I put 9 and print f. Okay, this one is better. Okay, that's a tail recursive sum. So sum of 9 is 45. Same. Let me do this. For integer I equals 1, I less than 11, I increase, and then I put an I over here. So each I take sum to I. Okay, and this one I push back a little bit. Okay, I got a sum from 1, 3, whatever, right? Okay, now let's look at the code. This one is called tail recursive function. So originally I want people to call this one, right? Sum of 9, sum of 10, something like that, right? But it's not tail recursive, so it's actually slow. It actually is quite slow, you know. So I don't like it. So I want to write something called tail recursive. Now let me tell you how to write this tail recursive. Number one, I have an accumulator here, sum. The sum term S actually show for sum. So if I have a 10 coming in, right? And initial sum I set it to be 0, right? So my sum actually is sum plus 10, right? And then my accumulated the sum. So my original sum 10 will call sum 9 with the sum 10 now. And sum 9 with actually call sum A, 9 plus 10. And then sum 7 we call A plus 9 plus 10. And then continue until I have sum 1 that's called sum 1 plus 2 plus blah, 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 plus 2, 10. And then I call sum of 0 that return my sum. That's how this is a helper function. This one called helper function. It's to help the original sum function and make it faster to run. So the S actually keep track of the partial sum from the previous function code. Because each one in the middle, you have a sum plus n, right? Original, I have a sum is 10. Next one, sum plus 9, sum plus 9. Next one, 9 plus 10 plus 8, not the new n. You know, and keep passing it until you down to the base condition, you return the S, okay? So that one actually is a faster program. Now let's try, let me see. Because it's much faster. If here I try not 11, let's try this. I'm sorry, it actually, the stack is too small, so that's probably a too large of a number. So let's try this. You know, it's fast enough, but the system stack may be too small. Designed by Java, probably too small. Let me try this one. Okay, you see, quite fast. Okay, you actually just a blink of second tick, you actually get out of the sum for up to 1,000. Is that okay? This is called tail recursion, and this one is the original function. This one is the helper function. Two have the same name because they are overloaded. They are overloaded, okay? And then they have one just call the other one. You know, sum of 10 will call sum of 10 with 0. Initial sum is 0, and then you have the sum of 10, 0, it will call sum of 9 and 10. Your original sum is 0, 0 plus 10 is 10. So sum of 10 and 0 will call sum of 9 and 10. Sum of 9 and 10 will call sum of 9 and 10 plus 9, 19. Sum of A and 19. Sum of A and 19 will call sum of A and 7 and 27. 7 and 27. Keep doing that until you have a sum of 0, and then that one just return a sum. That will be the 55 that we want. Is that okay? This one we call it tail recursion, and this one actually, this tail recursion is AP problem, okay? It's not something that won't be tested. Usually this kind of problem is in multiple choice though. They don't ask you to write a program for this. But usually when it happens, it's actually happening in multiple choice. Okay? Any question for this? There are some more complicated one, but I think right now is probably too hard for you, and you probably first figure out how this works. Is that okay? Both of you, is that okay? Hello?
Oh, sorry. I thought I
Yeah?
was unmuted. So this goes like 1, 0 plus 1 plus 2.
Yeah?
Right. Yeah. Okay.
Are you okay? Are you able
Yeah.
to make it out? You know how you
Yeah.
work? Yeah?
Yeah.
So probably you can actually put some print in between, okay, to figure out what is S and what is N. Okay, that's one way you can trace it easier. Probably today we'll stop here. Is that okay? Okay, bye both of you.
Bye bye.